In this video, I'm going to use Wolfram-Cloud Mathematica to look at a problem I call like the perfect shuffle. So I'm going to have some list of numbers, or sometimes I'll say array, um, and I'm going to divide that in half. So if I'm using the numbers, and this deck has an even number, so I'll say it's 2n. So I'm going to take the first n and call them pile 1, and the second n elements and call them pile 2. And then I'm going to interleave them. So I'm going to get the first card from pile 1, then the first card from pile 2, then the second card from pile 1, then the second card from pile 2, etc. And I'm going to call that perfect shuffle. But then if I sort of take that, and now that becomes the deck, uh, and I repeat that process, like if I repeat that perfect shuffle process enough, then it we get back the original order. So I want to sort of perform that operation, and what uh, sort of a known uh, interesting sequence. It's in the on the online encyclopedia of integer sequences. Um, this this number of how many perfect shuffles restore the order, and how that depends on the size of the deck. I'll show you that the the numbers are sort of like all over the place. They could be, uh, for two decks, then the number can go from quite large to relatively small. Sort of jumps all over the place. Okay, so let's just so I have here a just a list. I'm just sort of hard coding a list of 10 to sort of get us started. So I have a card. So this would be for me, I think I would call it n equals 5. So a deck of 10 cards. Um, and now I'm going to uh, have cards 2, which is going to be, I'm going to have the original deck cards and get from it a cards 2 that is going to be shuffled in this way. So I'm going to go through all of the cards and sort of do in a sense, I'm looping over sort of cards 1 and cards, I'm looping over cards 1, the original cards, because cards 2 doesn't have a length yet, but I will be making cards 2 as we go. So if the position is odd or even, I'm doing something different. That's the interleaving. So if it is odd, and I'm starting at 1, if I so it's not the same kind of indexing I would be doing if I were in Java or JavaScript or Python or anything like that. I'm starting with a 1. Um, but if the index is odd, I'm taking from the sort of pile 1, and otherwise I'm taking from pile 2. And pile 2 starts at sort of the lengths of the card divided by 2. So that's me taking from the second half of the deck. This is me taking from the first half of the deck, what I called pile 1 and pile 2. And then I'm printing it and asking, uh, are cards and cards 1 the same? And this kind of comparison, and we'll see below, but the answer is going to be no here, but we'll see down below that the answer is sometimes yes. And one thing just to point out is that this sort of simple equal between uh, these are lists here, but there could be shallow compares and deep compares. Are you just saying, are these two things pointing to the same memory location, or are we actually comparing two different things but comparing them value by value? And this is doing sort of what I want, the sort of the deeper compare. They may be in different memory locations, but are they do they all have the same values? And so this is just a single shuffle. So you see I broke this up 1 to 5 and then 6 to 10. And then I took the 1 from the first pile, the 6 from the second pile, then the 2 from the first pile, and the 7 from the second pile. And the 1 and the 10 always stay in the same place, but the others are moving. And sort of says, no, they're not the same. Okay. Um, so now I'm going to do multiple shuffles of the same deck, but I'm going to uh, get the deck. Instead of hard coding the deck, I'm going to use range 10. That's going to make a list for me of numbers 1 to 10. I'm going to be counting the number of times I shuffle, and I'm going to have, in this case, sort of 3 arrays. I'm going to have a card 0, which is sort of my original order that I'm not going to touch. I could also just, resurrect it anytime I wanted, saying by range 10. I'm going to have cards and cards 2. So cards 2 is going to be the shuffle version of cards. And then when I'm done shuffling, I will set cards equal to the cards 2 and sort of repeat. Okay, so this for loop is the shuffling of a deck of cards. I'm going through all the cards and getting my new shuffled order, perfect shuffle order. And the while is I'm repeatedly going through this shuffle, and I want, is the new arrangement, while the new arrangement is not equal to the original arrangement, then I will keep going. And I will be incrementing my shuffle counter, and this is me setting the new arrangement equal to be the deck of cards so that I can continue in my loop. So after one shuffle, there is the 6 in the second position. Then now after another one, it's going to be 8. After another one, it's going to be 9. Then it's going to be the 5. Then it's going to be the 3. Then the 2, and they're back in order. So it took of my card with n equals 5, my deck of 10 cards. It took me 6 perfect shuffles to restore the order. Okay. So now I'm going to add another loop where the number of cards in my deck is going to be changing. So I'm going to, and my number of cards is always even, so K is sort of half the number of cards in the deck. And I'm going to start with a deck of 4 cards, then a K of 2, because with 2 cards in the way my rules work, the first and the last card never shuffle. So a deck of cards 1, there's never any shuffling. If K were 1, if there were 2 cards, I would keep the first card in its position and the last card in its position. So if there are only 2 cards, no real shuffling occurs. So I'm going to start with K equals 2. Okay, I'm going to go up to 250. What I'm going to collect here in results are like these, I'll call them a tuple, the K and the number of shuffles to restore the perfect order. Okay, so we've seen sort of the insides of the loop we've seen before. Now we're just adding a loop over the Ks, the size of the deck, and we're adding to our results the results of the shuffling. And so here we go. Okay. And I'm using just like the free Wolfram-Cloud online. So there's some limitations on how much I can sort of do for free. And there is this while loop. And so sometimes it's sometimes the shuffling is quick and sometimes it takes a little bit longer. As we'll see, it's a little um, erratic all over the place. Um, and but there it is. So that was up to 250. And here are the results. And then we can just plot them. Okay. And we sort of see these lines. I'm going to sort of pick out some of these lines. And again, this is a sequence of around about which sequences been played with before. Some things are known. There are some conjectures. Just sort of playing with Mathematica. Okay. But we can sort of see these lines. I'm going to sort of pull out the lines. It is, if I say that this is X and Y, it is easy to pull out the relationship of the X to the Y's. What is harder is to figure out, and I haven't figured it out for the most part, what are the X's that fall on this line? Okay. Um, but that first, what I'm calling the upper bound, as far as I see, I've never seen anything above this line. Um, and the sort of equation for that line in sort of where I started, what I called X. And again, that was sort of half the size of the deck and starting at 2. Um, and then the Y was the number of shuffles to get it back to perfect. That upper bound seemed to be a 2x minus 1. So just plotting that function. And then the smallest numbers occur, we'll see that they occur for when the deck is, when my n or x or whatever I'm calling it is a power of 2. If it's 2, 4, 8, 16, then the deck gets back in order quite quickly. And that's the one place where I know, not only do I know the relationship between X and Y, but I know the X's that lead to it. And as we just said, the powers of 2. So this is a logarithmic relationship. And I made that in green. And now I'm just adding this sort of lower bound and upper bound to my data. And there we go. And then I can make that, stretch it out and make it larger. And we can see there are a couple of points that are just shy of this upper bound. And there are a couple of points that are just over this lower bound. But we do seem to have this sort of upper and lower bound. Um, at least, again, I don't know the x's that fall on this upper bound, but I seem to know the relationship between x and y. And down for the green, I know both the relationship of x to y and the x's that fall on that. Okay. I can use, and again, I'm just sort of playing around with Mathematica here. So I can use its select method. I can select from results. This pound sign sort of corresponds to the element in result, and my elements are tuples. So this is I'm going to pick out elements from results where the first part of the tuple times 2 minus 2, that was my upper bound rule, is equal to the second part. That sort of, so this is this pound square bracket 1 is sort of my x, and this is my y, and then I need this ampersand. It's just sort of part of the select syntax as far as I can see. And so this is me just using select to pull out those points that are on the red line. There are some what I'm calling consecutive sort of paired paired consecutive results, 6, 7, 30, 31, 90, where am I at? 90, 91, 210, 211 in here. And they seem to, the first number seems to satisfy n plus 1, n plus 2, n plus 3, all divided by 4. I have not taken, I think the next one in there would be in the 400s, and I didn't go that high to test if that's really a pattern or not. And there was another consecutive one in here. Where was it? 174, 175, and that seems 174, 175. I'm not even see. Yeah, 174, 175 are here. I'm not finding that they're part of that pattern. So I don't know if that's a pattern or not, but worth investigating perhaps. Okay. Here I'm using select again to pull out that sort of lower bound. So here are the things that obey the lower bound. And then here, not only do we know the relationship between x and y, we can easily see that the x's that satisfy this are the powers of 2. Okay. There was another one more line on this graph that I can add where I know not only the relationship of x to y, but I know the x's, and those are the ones that sort of lie right above, right next to the ones that we just saw. So here the numbers, the result is sort of twice. So if our x is sort of one more, or so I'm subtracting a 1. Let me go up here and it may be clearer if I point it out. Here was 8. That was a power of 2. And then we got our 4. And then next to it was 9. The next number was 9, which gave me an 8. Here's 16, which gave me 5. And the next one was 17 and gave me 10. 32. The next one was 33 and it gave me 12. So the sort of next one down seems to obey a simple rule as well. And I call that lowers 2. And that seemed to be 1 more than 4, 1 more than 8, 1 more than 16, 1 more than 32. So another sort of pattern where I understand the x's. I can plot that, and we see there are a number of points on that line. I can plot that, and then I'm going to add all these little things to my overall plot. There seems to be there are 1 or 2 stray ones here that I sort of struggled more with, but then there seem to be these lines where there are bunches of them. And so and they all seem to have sort of relatively nice, simple, fractional slopes. So here's a slope that was sort of 4/3. There weren't a lot of points on this one, but it did seem to be a sort of recognizable line. So I'm plotting it. It's just plotting that function so I can add it. And then, but I'm also doing my select with that rule. So this is a line with a slope of 4/3. And there seem to be a number of solutions on that. And then here is my upper bound had a slope of 2x. So I called this one, the next one, sort of half upper because it had a slope of 1. So here's a plot of that, and I'm going to put these plots, all these little extra lines onto the overall data, so you'll see them going through the data points. And now here is me using select, and this has a lot more points going through this. Here is another line with a slope of 2/3. seems to have a lot of points. So that's me selecting it. Here's me plotting it. And then here is a 4/5. So there again, there just seem to be these lines with sort of nice, relatively simple, rational slopes that go through our data. So now here I'm adding the data and the upper and lower, which you already showed, and then the lower, the other lower bound, the sort of next lower bound, this sort of, what was it, 4/3 and one, slope of 4/3 and one, and so on. Okay. And then here it is, and I just sort of pull it up a little bit. And we see, I have these lines that go through lots of points. And there's some in here that I did not get, but, we can probably grab a few points and figure out a nice rational slope and get them. So again, I don't have any, I can find relationships between X's and Y's. I do not have any feeling for the X's that do this. Okay. And here is just at the end, pushing, I wanted to get some tests, some results to push it a little bit further. And so I went up to 250. Now I'm going to start at 250 and get more of them. And I just changed the name of results so that I wasn't, and then I could sort of merge my results and results two, and then I'm going to have a three, but I'm not going to really do anything with it. I'm just showing you that, I sort of hit a limit. 250 wasn't maybe as high as I could go, but it was close to as high as I could go without overburdening sort of the free version of Wolfram-Cloud. But I can sort of push myself farther by just sort of starting my loop somewhere other than two. So I can get from, this was 250 to 300. And then down here, I don't know, then I'll bother running it if it's going to take a while. But here was me going from 300 to 350. So I can sort of get higher without running into the limit that it puts on me. So that just finished. I won't run the next one. It will take about the same amount of time, maybe a little longer. All right, that's what I wanted to just show you. Some just playing around with Wolfram-Cloud, sort of fun problem that produces a sequence that has been known and studied. Some things are known about it, but I don't think everything. Kind of the values kind of jump up and down. Some things are sort of easy to understand, this sort of power of two rule. And I don't know, just some fun playing the useful select method, pulling out the points that fall on the line. There are clearly lots of lines in there, but so it can be useful to sort of pull out which points are on which lines, and this select method is nice for that. Okay, that's what I want to show you on this one. Thanks for your attention.